Our 9-2 notes will focus on the area of a regular polygon. We have three definitions to start off with. First off, a polygon with congruent sides and angles is referred to as a regular polygon. Note that a square and an equilateral triangle are both examples of a regular polygon. The distance from the center to a vertex is actually referred to as a radius in a polygon. And the perpendicular distance from the center to a side is called an apothem. It's very important that you note the difference between a radius and an apothem. Visually, here's what we're looking at. Here we have a hexagon. The radius is any of the blue dashed lines that stem from the center of the polygon all the way to a vertex. An apothem is going to stem from the center to a side. Please try to keep these two straight. A radius goes to a vertex, an apothem goes to a side. Right underneath this picture, I have a list of polygons and the number of sides. This will be important because in this section, a random polygon will show up and you'll just be expected to know the number of sides. So for example, if you see the name heptagon, you should automatically know it has 7 sides. And this leads us to the area of a regular polygon. In this theorem, it gives us the area of the regular polygon as A equals 1/2 A times P, where A is the apothem and P is the perimeter. Rather than finding the perimeter separately, I'm going to rewrite this formula as A equals 1/2 A NS, where NS will calculate the perimeter so that we don't have to do it in 2 separate steps. The A represents the apothem of our polygon. N represents the number of sides, and S will represent our side length. If we can identify all 3 of these components, we'll be able to easily calculate the area of a regular polygon. So let's go ahead and take a look at some examples. Example 1 wants us to find the area of this regular decagon. So this is a polygon, so we know we're going to use the formula 1/2 ANS. Let's see if we can identify all 3 of these letters. The apothem, our A, is the length from the center to a side. And here in this picture, it looks like the length that is perpendicular to the side is going to be 12.3. So this is going to be our apothem. Our N is the number of sides. While it doesn't necessarily state directly what the number of sides are, we can get it by one of 2 ways. Either by counting the sides in our diagram, if possible, or this word actually tells us the number of sides. If you refer to the table on the front of the set of notes, a decagon refers to a polygon with 10 sides. So this means that N is equal to 10. So we have our A and our N. Last but not least, let's talk about the side length. In our diagram, it appears that our side length is given as 8. So this is our S. So we have our A, our N, and our S, and all we have to do is simply plug in these numbers into the formula. So 1/2 A, 12.3, times the number of sides N, 10, times our side length, 8. Now that we have all of these values in our formula, let's go ahead and calculate them. 1/2 times 12.3 times 10 times 8 gives us 492. And once again, since this is an area, our unit should be in square units. So that was a relatively easy problem. However, you know that these problems are going to get tougher. So let's take a look at problem 2. Problem 2 says that we want to find, it tells us that the side of a regular hexagon is 6 feet. So this is going to give us the side length S. So right now we know that S is 6. In addition, because it gave the word hexagon, and also because the diagram provided is a hexagon, we also know that the number of sides is also 6. And we want to find the area. In our apothem formula, we needed A, N, and S. Unfortunately, we're missing the apothem, the A. So let's actually use our diagram to find the apothem. First thing I want to do is go ahead and sketch my apothem in. So here's my apothem, our unknown. So how can we find our apothem? Well, just like our previous section, anytime we're missing a side, we typically try to look for a right triangle that includes that as a side length. So, what right triangle uses our A as a side? The right triangle, which includes the radius. So, here's our right triangle. What else do we know about this triangle? It looks like, just glancing at it, that we don't know anything. However, if the entire side of a hexagon is 6, and this is indeed a regular triangle, the apothem will split the side equally, giving us a short side of 3 in this particular example. So this actually gives us our short side of our right triangle. Now, one side alone is not enough information. We either need another side or another reference angle for this triangle. It turns out that we can find our reference angle by thinking about how many of these little triangles are within the entire hexagon. You could actually sit here and sketch every single triangle within this hexagon if you would like. But it turns out in every polygon that there will always be double the number of sides of triangles inside. And because an entire rotation around a center point is 360 degrees, you can always calculate this angle by taking the entire measurement all the way around 360 and dividing by double the number of sides. So in this case, we're going to take 360 divided by 12 because there are 6 sides and double it would be 12. If you take 360 divided by 12, this will give you the angle measure right there in the top by the center. In this case, it turns out to be a 30-degree angle. So this tells me that this is actually a special 30, 60, 90. I'll give you a hint. Every time you have a hexagon, this triangle formed with the apothem will always be a 30, 60, 90. In addition, in an equilateral triangle, the apothem will form a 30, 60, 90 triangle. Squares will actually create a 45, 45, 90 triangle. You may want to write that down on the side just as a reminder so you don't have to think about calculating this angle separately. I'll say it again. Hexagons and equilateral triangles will be 30, 60, 90. Whereas squares will be 45, 45, 90. You could prove this with this same formula to calculate that angle. Most students just do best by memorizing which particular special right triangle is in that particular picture. We're not going to solve for missing information other than in hexagons, triangles, and squares. So that's the good news. We're going to stick to our special right triangles. Okay, so here we have a special right triangle, 30, 60, 90, and we need to find the apothem. So we have the short and we want the long. If you take a look at your special right triangle formulas, for the 30, 60, 90, we have the equation short times radical 3 equals the long. We also have short times 2 equals the hypotenuse, but I don't really care about the hypotenuse in this particular problem, so I'm only going to use this problem. So our short is 3, radical 3 is part of the formula, and our long is the apothem. So this tells us that our apothem is 3 radical 3. Giving us our a value, we have our n value, we have our s value, and we're ready to solve for our area. Area equals 1/2 a n s. Let's plug in our values. 1/2, our apothem, 3 radical 3, and notice that I'm keeping it exact as long as possible. Our n, the number of sides, happens to be 6. There are 6 sides. And our side length happens to also be 6. So when I simplify this, I see I have a radical on the inside. So I'm going to multiply all of the numbers on the outside. 1/2 times 3 times 6 times 6. Because multiplication is commutative, I could swap some of these and move things around because it's associative as well. I'm actually going to cut the 6 in half first. So 6 cut in half is 3. 3 times 3 is 9, and then 9 times 6 will give me 54. So that's the value in front, or you can use your calculator to go ahead and calculate that. And then I did not use the square root, so I'm going to go ahead and just tack it on now, square root of 3, to get my exact answer of 54 radical 3. And this is an area, so it will be feet squared. Now, if you do not prefer a radical answer, you could of course find the decimal equivalent. So let's see here, I'm going to do 3 and then take a square root. Unfortunately, this calculator does not do order of operations, so I have to kind of do it in a little bit of a different order. And then multiply by 54 to get an exact answer of 93.53. Either answer is acceptable. So you could get the decimal equivalent or the exact answer. Just be careful if you're doing decimals. Don't round too much, especially mid-problem. All right, so let's take a look at one more example. The radius of a square is 4 inches. What is the area of a square? So this particular problem did not provide a diagram. So the first thing that I might do is go ahead and sketch in a square. Because I'm not the best at sketching with this tablet, I'm going to go ahead and steal my image maker here and get a square. And this time I'm giving the radius. So the radius is actually going to be the measurement from the center to a vertex. So it's this length right here. So we have a 4. Okay, so here's our figure. What do we know? Well, since it's a square, I know that we have 4 sides, so my n is 4. And it gives us the radius, which is not the side length. So I don't know the side length, and I don't know the apothem, so I actually don't know either of them. So let's turn back to the diagram, and let's sketch in the apothem. So here's my apothem, and then the side length is this whole entire length here, side. Okay, so once again, when I'm looking for some missing pieces, I'm going to look for a special triangle. As I had mentioned in the previous problem, in a in a square, this will always be a 45, 45, 90 triangle. You can prove this once again by taking the entire measurement around the center and dividing by double the number of sides. So since there are 4 sides, I would divide by 8. If you do that, you would get 45 degrees. So this is indeed a 45, 45, 90 triangle. Okay, so how do I find these lengths? Well, in a 45, 45, 90 triangle, I know that the leg times square root of 2 will always equal the hypotenuse. In this case, the leg is going to be my apothem, and the hypotenuse is going to be 4. So let's go ahead and solve for A. To solve for A, I have to get rid of the square root of 2 by dividing it. This gives us an apothem of 4 over radical 2, and because we typically don't like our radicals in the bottom, I'm going to go ahead and rationalize. And this is a technique we learned back in a previous unit. The numerator, we have 4 radical 2, and the denominator, radical 2 times radical 2, gives us a regular 2. Simplifying just a little bit more, the 4 divided by 2 will give us a 2 radical 2. So here's our apothem, 2 radical 2. Great, so we have our apothem, our number of sides. The only thing left is to find the side length. So the side length is actually not part of this triangle, but half of the side length is. It's the other side. The other leg in a 45-45 should match the apothem. So since the apothem is 2 radical 2, I know that this part of the side is also 2 radical 2, which tells me that the entire side length should be double the apothem that we have, or double the other leg, 2 radical 2. So 2 times 2 radical 2 will give us a side length of 4 radical 2. Now we have our S. We have our A, our N, our S, and we're finally ready to find our area. By the way, you might say, why are we using this complicated formula to find the area of a square? Why couldn't we just do side squared? And the answer is you absolutely could. I'm just trying to stick to the same formula in this section so that I don't confuse you by slipping something else back in and possibly confusing you more. So let's go ahead and plug in what we know. The apothem is 2 radical 2. The number of sides, since it's a square, is 4. And the side length is 4 radical 2. Simplifying everything on the outside, we have 1/2 times 2. That gives us 1. Times 4, 4. Times 4 is 16. So the numbers on the outside give us 16. On the inside, we actually have 2 radical 2's. So a radical 2 times a radical 2 is radical 4, or just a regular old 2. So it turns out the radicals completely cancel out, and we just have a nice answer when we multiply the 16 and 2 of 32 units. And once again, since we have a square area, we need square units, so we have inches squared. And 32 inches squared is our final area.